Now that we have an expression relating velocity and angular velocity, v equals r omega, we're on our way to having an angular form of kinetic energy, 1/2 mv squared. In fact, you might think we're already done. Just substitute in for v. So 1/2 mv squared becomes 1/2 mr squared omega squared, right? We are close, but it turns out we have to consider something with that mass term. If the body is rotating, doesn't it matter how the mass is distributed in terms of distance from axis of rotation? If you have a spinning chair, go ahead and try this. Spin yourself in your chair and bring it all your limbs as close to your body as possible. Then, while still spinning, stretch out your arms and legs as far away from your body as possible, or lean back your chair all the way. You can keep stretching out and pulling in, and you'll see something. The more mass that is closer to the axis of your rotation, the faster you spin. The distribution of mass from the axis of rotation clearly contributes to the kinetic energy, the energy of motion, of a spinning body. So how can we account for this in our expression? We'll do it with a new quantity called moment of inertia. We'll start by thinking of a body of mass as being made up of many particles, with masses m1, m2, m3, at distances r1, r2, and r3. And those distances are from the axis of rotation. So when the body rotates, all particles rotate at the same angular speed, omega, and the speed of the ith particle is v sub I, which is equal to r sub I omega. They all rotate at the same angular speed, but their distance is different from the axis of rotation. And so our 1/2 mv squared for kinetic energy actually seems to become 1/2 m I ri squared omega. And the total kinetic energy of the body is the sum of kinetic energies of all of its particles. And so that would be the sum of this over all I. And we can bring the 1/2 out. mi ri squared. Oops. Yeah. Like such. The summation in the parentheses is what we call the moment of inertia. So this quantity here. And that's denoted by I. So I is equal to moment of inertia. And it's for a specific body at a specific rotation axis. So it's the summation over I of all the particles that make up the object, r sub I squared. Notice I said for this rotation axis. So if the body is rotating around some new axis, the mass distribution from this axis will be different, and the moment of inertia will be different. The term moment is an unfortunate word to have in the name of this quantity, as it has nothing to do with a moment in time. So some physicists call this quantity the rotational inertia, which I think makes more sense, but it isn't the common name for it, so beware. So now with this new term, we can finish out our expression for rotational kinetic energy of a rigid body. It is, so K, rotational kinetic energy, is 1/2 I, moment of inertia, or rotational inertia, omega squared. And because of the way that we defined things, omega, rotational velocity, must be measured in radians per second to produce K in joules.